In the next section, I want to come to visit a problem that is almost as old as algorithms are, but also one that specifically randomization has a key role to play in. That's the question of deciding whether a number is prime. Before we'll come to that, a few comments on the design technique that underlies the algorithm we'll look at. And that's this aforementioned abundance of witnesses. So again, framed it again a bit from the complexity theory perspective. If you have some language in NP, then you know there must be some certificate for every word in the language that certifies that that's in the language. If we have that certificate at hand, then it must be efficient to check. Now, in general, this is not always true for everything in NP, but suppose that it is true for our specific language, that there are many certificates that actually show that X is in the language. That's an assumption we're making here, but we'll see examples. If that both is true, then it makes sense to try to just randomly guess some string and check if it is a certificate. Maybe we're lucky, and then we'll quickly prove that X is in L. And if we've kept going for a while and we couldn't find any certificate, then maybe we can conclude X is not in the language. That's the idea in abundance of witnesses. You hope you have a language in NP where there's many certificates, and so either you find one, or if you don't find one, there's a good chance that there is none. So the input is not in the language. And let's apply that to a more concrete problem. So given some number n, all we want to know is that a prime number or not? It can be traced back a lot in time. People wondered about this for a long time, and it's only fairly recently been properly resolved in a way. Let's first look at some simple approach that you've probably seen in some introductory classes, often a good intro algorithm. How do we find out if a number is prime? Well, if we've tested all potential factors and none of them divided the number, then clearly it is a prime. And more specifically, we can test all prime numbers below square root of n. These are the only actual candidates or the only interesting candidates for factors. The number might have more factors, but if it has any factors, it will have one of those, a prime number below square root n. Right? Square root n is clear. Any factor will be either below square root n or number divided by the factors below square root n, so checking for one of the two is enough. And we can restrict the attention to primes, because if there's a non-prime, then it has a factor, and then we could have, well, taken that factor instead. But in a way, this sounds like we're trying to solve the problem by solving the same problem, which sounds a bit contradictory, right? We need to know we need to know primes to check if a number is prime. But of course, there's no contradiction, because you can do an inductive algorithm. And in particular, there's a clever algorithm you will have seen, the sieve of Eratosthenes, which gives you all the prime numbers up to a certain threshold in a somewhat reasonable running time overall. And here's the algorithm itself. It's basically, it's called a sieve because it goes through all the numbers and kicks out those that are composite, that are clearly not prime. And it effectively goes through the numbers from small to large and then crosses out all multiples of a number. You can be a little smarter. So first of all, you iterate over the numbers, but then if you already know that a number is prime, then you have to do it. Otherwise you don't, because you'll have a factor that already crossed out all your multiples. And also with the multiples, you can start at the number itself. So you start with the square of the number, because all smaller multiples will have been caught by the smaller multiple as a number. Think about it for a minute and you'll see why. So that's where we can start, and we go up to a point where we would overshoot n. And then we take the product, the multiple of I, and mark that as not prime. And then if we've done all that, everything that is left must be a prime number. So that's finding primes up to a threshold. If we want to test the number for primality, what we do is we compute all the prime numbers up to square root of the number and test all of them. Easy. How good is this? The time of the primality check clearly is dominated by finding the primes. And how long does that take? It's actually a subtle analysis, if you want to be precise. So the time to find all the primes up to number m is, well, m for going through the loop, the outer one. Sorry, for, yeah, up to n, but I'm setting m as square root n. So you go through this loop m times roughly, and then for each prime, you have to go through that many iterations of the inner loop. I'm kind of not analyzing the starting at I part. That one is a clever trick, but I'm just ignoring that here, so it's just an upper bound. But doing this sum where you have to do a summation where you only do the prime factors, that's tricky. So we can make our life easy and get an upper bound by dropping that restriction. And then at least you get harmonic numbers, so m log m time. Sounds not too bad if you write it that way. And if you do actually make the analysis more careful and take into account that you only have the prime numbers here, you can show that it's m log m, really. That seems to be more technically involved, so we're not going to do it. And the space, of course, is maybe practically speaking more of a problem. Now, all of this sounds okay, right? M log m, we've been happy with algorithms of that running time. But of course, the problem is here that this is a number, and we would encode that in binary. So even square root n is an exponential in the actual input size. And I think if you take this primality check and apply it to prime numbers as you would use them in cryptography, it's not going to be good enough. You need some smarter techniques. Okay, but that's kind of the trivial algorithm to do it would work like this. And it's not completely useless, but it's going to be exponential in the input size. So the question then quickly comes up, can we do much better? What's the complexity status of these problems? And so with these problems, I've not defined the problems. Let's do that here. There's two problems. There's the problem primes. If you think about a language, that's the set of numbers that are prime. So we're given an integer in binary, and we want to check yes, no, is that a prime number? And you can also use the search problem of this decision problem, the integer factorization problem, where you're given an integer, but then you either want to find some non-trivial factors, which prove that the thing is not prime, or you output it's not prime, it's prime. In which case, we don't require a certificate in the problem of integer factorization. Okay. As you may see from this immediately, if the number is not a prime, then the factorization is a certificate. So we can conclude that primes is in co-NP because the no instances have an efficiently checkable certificate. What's not clear is if the yes instances also have a certificate. How would you prove to me that a number is prime other than saying, I've tried all the factors and none of them I've tried all the numbers and none of them is a factor? That seems less clear. So whether primes is in NP is already a bit unclear from the definition. Also a good point to make the connection to the very far beginning of the lecture. The running time of the sieve of Eratosthenes is, of course, pseudo-polynomial. Right? It's polynomial in terms of the number of things in the input, but it's only pseudo-polynomial if you take the binary encoding. Now what we'll show is a slightly better result. So here, the fact that it's in co-NP is not practically useful, right? We don't expect efficient algorithms for all problems in co-NP, same as for NP. But we'll show that you can do a randomized test, a randomized primality test, or compositionality test, I should say, which also shows that the problem is in BPP. And we've already seen BPP is likely to be the same as P. Now, in this case, we don't actually need to invoke these kind of arguments. If you're just curious about the complexity status, it's been in this millennium, but a while ago by now. As a major breakthrough, we know now deterministic, unconditional algorithm that runs in polynomial time and decides whether a number is prime. And there's also a notion of certificate, in a way, that the algorithm can prove to you that a number is prime without just exhaustively going through all factors and showing that these are not numbers and showing that these are not factors. There's clever number theory behind it. Crucially, this is not clear for integer factorization. And everyone working in cryptography knows that the classic cryptography really relies on factorization being hard. We know that it is not hard on quantum computers in the theoretical way to define them, which I think the largest number factorized on a practical quantum computer is 6 or so. It's they're not quite there yet. But in terms of the computational complexity, we don't know. Integer factorization seems hard, but we don't know. Maybe it could be in some sneaky way allowing us some efficient algorithm, and we just haven't found it yet. That's just as an aside. So what I'm showing you is not the state of the art. For checking primes, in principle, you can do deterministic polynomial time. Now, the algorithm itself is complicated enough, and I think the degree of the polynomial is n to the 6 or so, and it's not clear if you can do this much better. So practical implementations will very much use these randomized algorithms that we'll look at, or slightly cleverer twists of those. So does primes have this property that we have an abundance of witnesses? Let's try the obvious. And really, I should have said not prime here. Because, as I said, there are certificates for primality, but these are tricky. So what I mean is, can we expect to easily find factorizations for a non-prime number? If we just look at the factors, the obvious approach to certify that a number is not prime, that's not going to work, right? There's numbers that are just there's composite numbers with just 2 large primes as a factor. And so finding these is needle in a haystack. That's not going to work with randomly guessing numbers. Also, that's hardly or it's hardly a promising approach. Because if that was possible, it would give you a factorization. Right? If I can guess a factor, then I can produce the two. I can produce a factorization of my number, proving that it's composite. And we've just discussed that that is unlikely, or seems hard to do. So we have to work harder, and we'll have to use something that indirectly certifies that a number is not prime, but without explicitly giving you a factor. That's weird. How would that be possible? Well, enter number theory and modulo and then finite fields and so on. There's various tools you can apply there. The simplest is Fermat's little theorem, which just states what is written here. For every prime and a number between 1 and the prime, you could check that the raising that number to the prime power -1 is going to be equivalent to 1 modulo p. And so I'm not going to dive into any of the number theory parts here. So we could try to pick a random a in the range. So we're given some number p for which we want to check if it's prime. Right. So I guess checking means we compute this power modulo m, modulo p. And this exponentiation sounds expensive, but you may know if you do it modulo p, there's actually efficient algorithms, because you can always do modulo p because it's a field, so you can compute in the small number field where everything is staying below p. So, and if that is not equivalent to 1, then we know p is not a prime. Okay. This is indeed sometimes used. It's called the Fermat primality test. It has one problem that maybe some people know about. This is an implication. If we have a prime, then this holds. It's not an equivalence. So given that mathematicians try to be as precise in general as possible, if it's not formulated as an equivalence, there's probably some counterexamples. And in this case, it's famous enough. These are called the Carmichael numbers. Which satisfy this but aren't prime. Let's just give that a name here so I don't have to copy it. So the primality test here is relatively straightforward to do, but it has this blind spot, or, well, infinitely many blind spots, where it would erroneously say something is a prime because this is satisfied, but the output should really be, it's either prime or a Carmichael number. So can we do better? We need a more famous mathematician. Let's use Euler. There's a criterion that's named after him, at least. If we have any odd number greater than 2, now this time it's a proper characterization. This number is prime if and only if the following is true. For all numbers so this is I don't know, it's the finite field of the integers modulo p. That's what I mean by this. So if we take any number not 0 and take that number to the p minus 1/2 power, so that's why p has to be odd. Otherwise, this is a bit of a trick, a problem in integers. Then taking that modulo p has to be either 1 or -1. And if that's true for all numbers in this field, then p is prime. That's an if and only if now. So it's a bit more convoluted how to use that. But at least now we could check this. We won't want to check it exhaustively because that's a lot of numbers if p is big. But we could check random a's and hope for the best, right? If we find an a where this is violated, then we immediately know p is not prime. if we checked a lot of A's and they all satisfied the criterion, we could try to do the generalization and say maybe all of them do it. So let's claim P is probably prime. Question? Yeah, I guess it's P minus 1. Just like I should probably have. There's no nice element symbol that corresponds to the equivalence. It's a bit more memorable to write it that way. Yeah, thanks. Please ask questions if it's not clear. Now this could work, but there's one catch, which is, does this have this property of abundance of witnesses? And that's where things get slightly tricky, but is not too bad. We'll just look at the easier part. So I'm assuming that I'm given a number that's not just odd, but also n minus 1/2 is odd. So it only works for half of the odd numbers. Then it's easy to show with this criterion that, well, first of all, if n is prime, then that has to be true for all of these guys. That's from above. But if n is not prime, then at least half of the numbers a from the set here give a result that is not in 1 minus 1. And so if I pick a random a, I have a chance of 1/2 to pick an element that shows this. Again, the proof is more number theory than algorithms. So I'm basically skipping this now for interest of time. You can show that you have some injective function from the numbers that are not witnesses to the set of witnesses, so you can pair them up in a way. And so the number of witnesses can't be smaller than the number of non-witnesses, where a non-witness here would be a number that's in this set, 1 minus 1, if you take the power. From this, you can build what's here called the simple Solarway-Strassen primality test, because it has this restriction that it only works for half of the odd numbers. This is a restriction you can easily lift, but again, it's more number theory than algorithms. The algorithm is as you would expect, as I described. You pick a random number from the allowable range, you compute this power modulo the number, and then just check if the number is in the expected set for a prime, then we output it's probably a prime number, and otherwise it's not a prime, and this is for sure. So it's basically we've already proven that this is a one-sided error Monte Carlo algorithm for the compositionality problem. So if I give you a composite number, you'll probably find it with probability 1/2. If it's not composite, namely prime, then you'll never gonna err on that. Now, one-sided error Monte Carlo is good, but for the wrong problem, for the composite problem. Now, if you want to formulate it as a primality test, then we can call it a two-sided error Monte Carlo, where the error is in the other direction. That's all that the corollary says. And this restriction is just a reformulation of this condition. I'm going to leave it with that because I'd rather show you some interesting algorithm for satisfiability. There's one last thing you can do with this, apart from checking for primes. You can also use this to find a prime number, or sample a random prime number, which is often a building block in other algorithms. The algorithm is relatively simple. We keep trying for a certain number of attempts. We generate a random bit string and interpret it as a number. It's a bit of a slightly convoluted way to say that we generate a random odd number, but I wanted to explicitly show that you can do this from random bits. Maybe this is not so surprising. Then we run the primality test also a certain number of times just to get more confident in the output. Probabilities boosting. And if any of the outputs says this is not a prime, then we try again. So we increase the number of failed attempts. And otherwise, we can output our prime number because we probably found one. Okay. And we fail if we've used up too many attempts. Let me state the theorem, but I think I'm also, in the interest of time, skipping the proof here. So the claim is that if I call this with twice the same parameter, then I get a two-sided arrow Monte Carlo algorithm for generating primes. Where I'm using I guess that's L here, where I'm using roughly L bits. Now, some of the leading bits could be 0, so I guess it's a prime number of value at most 2 to the L. What you have to show is, 1, that the output is usually a prime, and 2, it doesn't fail all the time. That's the 2 claims. The fact that it uses enough repetitions on an algorithm that has an error of 1/2 just means it's going to have an error of 2 to the minus k. Is actually stronger than what we would require for just Monte Carlo. And it doesn't fail with this statement, no prime number found. With the probability of 1 over 2L. So again, much stronger than what we need. So you could reduce the number of iterations if you just wanted the 1/2. The only interesting part is we're picking a random odd number. How likely is that to be a prime? Let's ignore the second part. We're also checking for primes with a potentially faulty method that sometimes doesn't. Which way around is it? It may sometimes say it's probably a prime, but it may sometimes erroneously say that. Okay, so it's a bit in the 2 directions. But let's suppose this test was perfect. How likely is it that we hit a prime number if we just randomly sample a number? So apart from the standard analyses we've done many times, So we actually force the first bit to be 1 here. So the n is sampled uniformly in the range 2 to the L up to 2 to the L minus 1 up to 2 to the L. So it's a random odd number from that range. How likely is that to be a prime number? And so this is where you need an ingredient from number theory again. And this, I think, is useful enough to at least roughly have in mind. So prime number theorem. You likely saw some statement of this in some introductory module, but often not formulated in the computer science-y way. Pi of x is a function which denotes the number of primes less or equal x. And the prime number theorem says that this is asymptotic to x divided ln x. Okay. And so, well, what does it mean? The fraction of numbers which are prime is going to 0 because out of x numbers, only x divided log n x are prime. But also is a fairly large fraction. I always found that surprising that there's so many primes. Also, the number of primes, if you look at the distance between two consecutive primes, this is like a very chaotic sequence. Sometimes you have these twin primes where the distance is just 2, and I think it's still open whether there's infinitely many of them and all these things. And then there's sometimes long jumps between primes. But if you smooth things out by integrating, just counting how many primes are before a certain point, then you get this fairly clean and simple description that at least asymptotically gives you a nice number. And so you can maybe now imagine you have from this range, there's going to be roughly 2 to the L divided L many primes. So you have a chance of 1 in L to pick one. So you have to sample L times in expectation to get one. I'm not going to do the full math here. It's something we've seen a few times now. So the overall running time for the algorithm, I think, is maybe useful just to state, because L to the 5th is also not that great. Okay. So I just wanted to throw this piece of knowledge out without much more content or more context.